Still in chapter 1.2, and we're going to talk about something really important that applies again to all of the functions that we're going to be looking at this year, and also is sort of a preview into calculus. So, the difference quotient. In Algebra 2, you might have learned a formula for the difference quotient and how to simplify it. And we're going to try to stress a little bit more about what the difference quotient is and what it's used for. So, the difference quotient is actually a formula for average rates of change. Remember, we already know a formula for average rate of change. It's change in y over change in x. And so this is still applying that formula. We're just looking at a function in a really general sense. So here's a picture. Average rate of change is slope, right? So we're trying to find the formula for the slope between any 2 points on f of x, not two specific points. Normally I say find the average rate of change between x equals 0 and x equals 10. Here we're saying find the slope, the average rate of change, between this point, which is f of x, and then some other point on f of x, which is h units away. So see how h is like this distance over here? Go h units to the right, land on that point, and what's the slope between those 2 points? A line that passes through 2 points on a curve is called a secant line. So it's a slope for a secant line between any 2 points. And if we look at the coordinates of the second point, so it's h units away, right? So whatever x is, add h units to that, meaning like go 5 to the right or whatever. And then the new f of x value would be whatever you get when you plug in x plus h. So we're saying, okay, the horizontal distance here is h, and the vertical distance is this f of x plus h minus f of x. So the slope for a secant line, I'm going to write m secant here, is equal to, let's take this first point as y2, f of x plus h minus y1, f of x, over, let's call this x2, x plus h, minus x1, which was just x. Simplify that a bit. F of x plus h minus f of x, that's the difference in the y values. And then this x minus x is going to cancel out. You're just going to get divided by h. So this gives us a formula for the slope between any 2 points on f of x. And the smaller h gets, the closer these 2 points get together. So as h approaches 0, the slope of your secant line approaches the slope of a tangent line. A tangent line is, here's f of x. What's the slope of a point that just shares that one point of tangency? What's the slope of this tangent line instead of the slope of a secant line? Well, we can't really find a slope of a tangent line just using the slope formula because we can't plug in 0. But we can get very close to it. What if h is something really minuscule and then our secant line is practically a tangent line? So that's calculus. The study of derivatives is looking at slopes of tangent lines to kind of put things very basically. Find the difference quotient and simplify the answer. Find the difference quotient, simplify. So apply this formula, simplify whatever you can. The formula first says f of x plus h. That means evaluate f when you plug in x plus h. So m secant is equal to, instead of 4x, it's 4 times x plus h plus 3. That's f of x plus h. Subtract f of x. Well, here's f of x. Subtract all of the 4x plus 3. So that's f of x plus h minus f of x. Divide the whole thing by h. Now, if we're doing our math correctly, it should be that all of our non-h terms cancel themselves out. So let's see what we get when we distribute. 4x plus 4h plus 3. distribute the negative through, minus 4x minus 3, all divided by h. Again, if you've done the math correctly, if you've properly plugged in x plus h, properly subtracted f of x, everything that doesn't have an h should cancel itself out. 4x minus 4x, positive 3 minus 3. I am just left with 4h divided by h, and that's good because I'm allowed to divide by h. So the slope of the secant line is the number 4. So the formula for the slope between any 2 points on f of x is 4, meaning the slope is always 4. Well, that makes sense because go back and look at this. This is a linear function. I didn't actually need the difference quotient to tell me that the slope between any 2 points on my linear function is 4. So actually, from here on out, if you see a linear function and it says find the difference quotient, simplify the answer, I want you just to skip to the final answer because I want you to make the connection between like, okay, this difference quotient is the formula for slope. I don't need a formula for slope for a linear equation. I can just show you what the slope is. I see that it's the number 4. If your function is not linear, it's quadratic, it's cubic, think about those graphs. I don't know exactly what this one looks like, but on a quadratic graph, the slope is going to change depending on where I put my 2 points. So I'm not just going to get 4 for this answer. I'm going to get something that still has an x in it and becomes more of a formula depending on what x's you're plugging in. Okay, so m secant. I've got to plug in x plus h. X plus h squared minus 2 times x plus h. This is f of x plus h minus f of x all over h. I find that if I have something more complicated to do, sometimes I forget to subtract f of x. So do make sure that on this step that you really are getting everything to cancel and you're not just saying it cancels, because that's how you can catch your mistake. We need to square out x plus h squared. Remember, you can use, well, I say remember, I've recorded these videos a bit out of order, so there's something called Pascal's triangle that looks like this. So on the diagonals are all ones as far down as we want to go. For numbers that fall between 2, you add these two. So 1, 1 is 2. Diagonal. Let's do one more round. 1, 1 plus 2 is 3. 2 plus 1 is 3. Copy down the 1. These are the coefficients for squaring a binomial. These are going to be the coefficients for cubing a binomial, so that's going to help on number 3. So what do I mean by this? I mean, if I've got x plus h squared, it's going to be x squared plus 2xh plus h squared. If that confuses you, this is honestly just shorthand for like FOIL it out, right? Or just multiply x plus h times x plus h. But we should be great with squaring binomials at this level. Distribute a negative 2, negative 2x minus 2h. Distribute the negative 1 through, minus x squared plus 2x all over h. Again, this is where you can catch mistakes, so be sure that you actually are getting things to cancel. Positive x squared minus x squared. That has an h, that has an h. Minus 2x plus 2x. There's an h there. So everything that still has an h can be divided by h. So I'll write this step out. 2xh plus h squared minus 2h. Don't forget about that one. All over h. You can divide every term by h. So the slope of the secant line is 2x plus h minus 2. It's a bit early in the year, but I know some of you are in Physics C. Eventually, you're going to learn about derivatives, and you'll learn about the power rule. And the derivative of x squared minus 2x is 2x minus 2. So the slope of a tangent line, if h is 0, is 2x minus 2. We will get into some of that at the very end of the year after our AP test. So again, this is a formula for the slope of the secant line, meaning I can pick any x on the graph. I can pick any point h units away, that can be to the right or to the left, and then I can calculate 2x plus that h minus 2, and that will give me the slope between those 2 points. All right, last one of these. Slope of this secant line, 2x cubed. I don't want to FOIL out x plus h times itself again. I want to use Pascal's triangle to tell me what the coefficients are going to be. So the first one, we've got a 2 out here, first of all. First one is going to be x cubed. And then this 3 is 3x squared h. The next 3 is plus 3x h squared. So the x is squared first, then the h is squared. And then the last one is for the h to the third power. Minus, don't forget to subtract, f of x. It's just one term. All over h. Again, I don't want to make any mistakes, so I'm going to distribute and show myself the distribution. It's easy to forget to multiply something out or just make a silly mistake, so just take the extra second here. So it is working out that 2x cubed and minus 2x cubed canceled. Everything else has an h in it, so it should survive. And then we can divide by h. So my final answer, once I divide everything by h, will be 6x squared, no h, plus 6x times h to the first, plus 2h squared. All right, so that's the slope of our secant line. Again, we can pick any x value on 2x cubed, any point that's h units away, maybe 2 to the right or 3 to the left, whatever, and it will tell us the slope between those 2 points. Okay, what we're going to be focusing on from here on out is domain and range. This is going to be what we're going to be spending a lot of time on for the next few days here. Domain, reminder, is the set of inputs for which the output will be a real number. That means we have some rules here. Some functions are easy. The domain for a linear function is all real numbers. There are no issues on a line, right? There are no vertical asymptotes. There are no holes. There's nothing to worry about there. Same for polynomial functions. Super easy. You can plug in anything into a polynomial function because those graphs go on forever without any holes or jumps or gaps or anything. Radical and rational are where we start introducing problems, because think about a radical graph, your traditional radical graph, something like that. It has a starting point and it goes off just in one direction. It does not go on forever in both directions like a line or a polynomial. So with that in mind, if we have y equals the square root of whatever, that expression underneath the square root, we have to ensure that we only put x values in that cause the expression to be greater than or equal to 0. We can only square root positive values or 0 to get a real number. Rational functions, think about those graphs. Again, we're going to get into all this graphing stuff down the road, but remember these from Algebra 2? They have vertical asymptotes, which means those are values, x values that never go into the equation. So when you have some sort of expression divided by some sort of other expression, it's the denominator that can mess things up, right? Whatever you have in your denominator, it doesn't have to stay positive, but it just can't equal 0. So it might be that, okay, x can be any real number except 3, because that makes me divide by 0 in the denominator. So we need to pay attention to what type of function we have, and then we can figure out our domain from there. We're going to use interval notation. So recall that interval notation is like parentheses. That doesn't include the value, and then square brackets. The number that's next to this is included. So I'm just going to write includes endpoints. How about that? And you could have combinations of parentheses and square brackets. State the domain of each function, write answers in interval notation. So this is a square root function. My rule for square root functions, not my rule, the rule, is that x minus 5 needs to remain greater than or equal to 0. Solve this little linear inequality just by isolating x, add 5 to the other side. As long as we pick x values greater than or equal to 5, we'll get real number outputs. And you can always test your domain. Plug some numbers in that fall into that category just to make sure. What does this look like in interval notation? It just means the domain is 5 to infinity. Include 5. You can't ever have a square bracket on infinity because that's not a number you can plot. That's just a direction that we're headed. Number 5 is rational. So again, it's the denominator that's the problem. Set 2x plus 1 not equal to 0 and solve for x. 2x can't equal -1. X can't equal -1/2. X can be anything except -1/2. So the domain can stretch from negative infinity up to -1/2, but I use a parentheses to say up to but not including that endpoint. And then I know that last year, depending on the program you used, you might have, like your online book, you might have been required to use union symbols. I don't care either way. I don't think our AP classroom has you typing this stuff in, but I don't think it cares either way. So use that if you want to. -1/2 to infinity is the other half of the domain. So basically, if you were finding your answer on a number line, the whole number line is shaded except for that one little point. Number 6, this is polynomial. No square roots, no denominators, no issues, all real numbers. This is the symbol set notation for all real numbers, or interval notation where the directions, so negative infinity to infinity. G of x is 10 minus x squared. That's quadratic, also known as polynomial. So no real issues. All real numbers is our domain. Number 8 is back to being a rational function. X squared minus 9 can't equal 0. Remember, we can factor this. I'm a big believer in factoring because I find that, and this is like an all-year problem, something that people tend to forget all year. If you add 9 in square root, people tend to forget the plus or minus. This is one where you would have x squared equals 9, x equals plus or minus 3. If you just factor it, it would be very hard for you to miss the fact that x is plus or minus 3. X cannot equal plus or minus 3. So careful on your domain for interval notation. You always start at negative infinity. What number do you hit first? -3. Here's the piece people forget about. Any number between -3 and 3 is also in the domain. Like you can plug in 0, for example. And then any number from 3 to infinity is in the domain. Here's an example of me not writing my union symbols. Again, I'm not going to count off either way. That's not something that's stressed on our AP test. Go ahead and write them in if you want. I'm sure your math professors would be happy for you to use proper set notation. And finally, number 9, 1 minus 3/4 x. Don't be fooled by the fraction here. This x is not down in the denominator. It's 3/4 times x. This is linear, also known as degree 1 polynomial. So, no issues, all real numbers for domain. So that's domain. We're going to talk about range. Oh, I have some of these other domain problems too. Sorry, we'll finish up. I got ahead of myself. What about even roots? Square roots, I said radical functions have to stay positive. Any even root has the same rule as a radical, as a square root. So 3 minus x needs to remain greater than or equal to 0. Now careful here. If you're solving for x, when you multiply or divide by a negative, that changes the inequality symbol. Why does it do that? Because think about if you didn't use this route. What if you instead just added x to the other side just to be done with it? Your inequality symbol is based off of where the x value is. 3 is greater than or equal to x is another way to say x is less than or equal to 3. So either way, your domain is negative infinity up to 3, including that endpoint. Odd roots. have no restrictions because you can odd root a positive, a negative, and a 0. So odd roots are falling in line with polynomials, all real numbers. Now, when you start combining roots and rationals, that's where you have to think a little bit more. The root says that 3 minus x needs to stay greater than or equal to 0. But the denominator says, yeah, but 3 minus x can't equal 0 either, because then you'd be dividing by 0. So when I see a root, an even root, and a denominator, I just say 3 minus x should just be plain greater than 0. 3 should be greater than x, or in other words, x should be less than 3. So negative infinity to 3 with parentheses. For number 13, we have a square root on top and an expression in the denominator. So not only can x minus 3 not equal 0, x needs to remain greater than or equal to 0 for the square root function as well. Okay, so we have x needs to stay greater than or equal to 0. So that's like 0 to infinity, right? But then we have x can't equal 3. So now we've got to make that cutout in our domain. Our domain is actually 0 to 3, not including 3, and then 3 to infinity. You have to simplify your domains if you're writing an interval notation. 4 is polynomial, all real numbers, no radicals, no fractions, no issues. 15 is an even root, so we have to make sure x minus 2 stays greater than or equal to 0, and it has a denominator with a variable in it, so we've got to make sure that x plus 5 is not equal to 0. So from here, x needs to stay greater than or equal to 2, so 2 to infinity. If x plus 5 can't equal 0, then x can't equal negative 5, but negative 5 is not in the 2 to infinity domain already, so we don't need to make an extra cutout for that negative 5 like we did in 13. So the domain is just 2 to infinity, which already leaves out the negative 5 issue. Okay, what about range? Range can be harder. Domain is hard in some cases. Range can be harder because there's not, it's not as easily like a set of rules as just kind of a checklist to run through. So once again, linear and polynomial are the easy ones. A line goes on forever in both directions. Range is all real numbers, unless it's horizontal. Polynomial function, end behavior goes on forever. You might need to find a max and a min, so you do have to be careful with this. It could be all real numbers, or if it's an odd exponent, or odd degree, right? Because you'll have end behavior opposite. Or if it's an even, you need the like min or max to plus or minus infinity. We don't have as much of this in just our straight up domain and range problems, mostly odd degrees that we'll be thinking about. Quadratics, we do have to think about this. For a quadratic, the range is either the vertex to infinity, or if it opens down, negative infinity to the vertex. So we'll have to figure out the vertex. For a square root function, remember its graph is something like this. So again, I'm not going to give you anything too complicated, but if the expression underneath the square root is linear, for example, it will hit 0 and it will go up to infinity. Unless we've put a negative or something like that. We might have to think about graphs for those. And then for rational functions, remember they have those horizontal asymptotes that help to dictate what y cannot equal. So we might have to think about these. So what I do for a lot of these, for radical and rational, I think about, can y equal 0? Can I figure out an x that makes y equal to 0? Can I think about plugging in different x values so that the overall y would stay positive? And can I think about any scenarios where y could come out negative? And that's how I figure out my domain or my range for these. So this is harder. You can see my rules are not as like easily black and white as what they were for domain. State the range. Okay, this is a square root function. It's just x minus 5. If you'd like to square root the graph, it's been shifted to the right 5 units. So that range is 0 to infinity. You can also find the domain and start plugging in domain values and just kind of see what happens. If you plug in 5, you get 0. If you plug in 6, you get 1. 7, you get square root of 2. It just keeps going up from there. 17 is rational, so let's just run through a checklist. If there's no x in the numerator, then there's no way that the overall fraction will ever be exactly 0. Think about plugging in 100 billion for x. 2 divided by 200 billion plus 1 is not exactly 0. It's just incredibly close to 0. So if there's no x, then y can't be 0. So already 0 is excluded from our range. Now the numerator is always positive. Positive 2. 2x plus 1 can be both positive or negative, depending on what x values you're plugging in. So yes, you will get y values that are positive, and you will also get y values that are negative. So the range is all real numbers except 0. That's the only number you can't achieve if you graph this thing. So negative infinity to 0, 0 to infinity. When you're first starting out, it is totally okay to graph these and see what's happening too. I think it's nice to connect the graph to the numbers to see what's going on. Number 18 is a polynomial. I know we have not talked about end behavior and degree yet, but we will be getting there shortly. And you may remember from last year, cubics have that end behavior, right? It's like something like this usually. Okay, so this domain, or this range, sorry, that's confusing. This range is negative infinity to infinity. If that were 3x to the 4th, I'd have some problems. I'd have to figure out minimums, but I'm not going to put you through that. Now, number 19 is quadratic. For this quadratic, it's best to think about the fact that it opens down and it's been pushed up 10. So it starts up at 10, and then it opens down. If you can do that, then the range starts at negative infinity and goes up to and including 10, but no higher than that. All right, what about the range of 1 over x squared plus 9? Go through your checklist like you did for 17. No x, so y can't equal 0. There's no way. This will be close to 0, but it'll never be 0. What about how it divides out? 1 is always positive. X squared plus 9 can certainly be positive. Plug in 0, 1, 2, 3. All those are positives. Can you ever get a negative out of x squared plus 9? If I plug in negative 500 billion and I square it, it comes out positive. I add 9, it's still positive. If I put in a negative tiny number, negative 1/4, and I square it, it's positive. And I add 9, it's still positive. This is always positive. So there's definitely y values greater than 0, but there's no way to get y values less than 0. So for our range, y cannot hit 0, but it can only stay positive from there. 21 is a line, linear, right? So the range is negative infinity to infinity. 22 is a cube root. A cube root, even though it's gradual, has this kind of generic graph. It will continue to go to approach infinity as x approaches infinity, and it will approach negative infinity as well. So that's all real numbers. Again, I won't give you even root problems that are too complicated, like a crazy expression underneath. If this were 4th root of 3 minus x, it would be 0 to infinity. 23 I have is negative 2 over 3 minus x. So no x, y can't equal 0. Think about the square root. This square root sign is only positive. If you plug in values in the domain for that, so like plug in 0, plug in 1, plug in 3, plug in -10, you're going to get the positive square root of something. So you have this always -2 divided by this always positive square root. That's always going to come out negative overall. So y is less than 0, but y cannot be greater than 0. So this range is -infinity to 0, not including. Okay, and our final one, I know this is a long day, our final one. Can y equal 0? Finally, yes, there's an x up here. When x equals 0, y equals 0. So yes, y can equal 0. What about the signs? We have another square root with a positive in front of it. So we have this always positive square root over this, well, x minus 3 could come out positive, or it could come out negative, depending on what you're plugging in there. Except, what can you plug in there? Let's think about this. Domain, x needs to stay greater than or equal to 0. X can't equal 3. So can I get negatives? Let's double check on this. If I plug in 0, yes, I get -3. If I plug in 1, I get -2. So yes, this scenario is possible. That's something to kind of consider. Consider the domain. Make sure everything's actually probable and possible. So the range for this one is yes, including 0. Yes, it can be positive. Yes, it can be negative. All real numbers. Again, on any of these, we can graph them to kind of double check, especially as we're first starting out. Domain is a big theme all throughout the year, and it's important to know for calculus too. Okay, that's a very long day of notes. We might end up splitting it up into 2 days or partially homework or something, but we'll spend a long time practicing this too.